get started. Are there any questions? Yes. All right. Does somebody have the practice exam or the old test?
Yeah, I have it right now.
Just read it out.
Oh, calculate the solubility of barium sulfate in water and at pH 2. I know the water part, but I can't do the pH 2. I don't know.
Did you get did you figure out the K? Well, if you want to figure out what the solubility is in at a pH, pH is, what does pH stand for? Power of hydrogen ions. It's actually the negative power, right? Negative the exponent. But it's a power function. But anyway, pH is going to be acid. And so the first step is, did you calculate the KSPA? Would be the first step. Well, what is KSPA? Somebody tell me what the KSPA is. Solubility in acid. So that's the first thing you need to calculate. What is the solubility in the acid? And so to do that, you would look at what gets attacked. You know, we see the solid barium sulfate goes into barium ions and sulfate ions here. What gets attacked in this equilibrium by acid? Sulfate. There's a lot of times people do this, you know, for whatever reason. What's the problem with doing this?
Doesn't take in concentration.
So many times people will do this on the test. On that test too. Lots of people, not lots, like more than I would expect. Like a couple of people did this, which is more than I expect. Because what's the problem with this here? It doesn't do it, you know, simultaneously. The two protons attack the sulfate, you know, in sync. Right, and so that was a common mistake on that test. Most people did it like this. And then what do you do next?
React one more proton.
React one more proton? No, we don't react one more proton.
Why?
We don't, even though it's a dibasic base, because how strong, tell me, how strong of a base is HSO4 minus, for one thing? You know, what's the KB for HSO4 minus?
Mom.
Very small, because its conjugate acid is H2SO4. In fact, we consider HSO4 minus not to be very basic at all, because it'd be in the same category as like chloride, bromide, iodide, nitrate. How basic are those? Neutral. And so, you know, we're not going to attack this with another proton, because it's like, okay, chloride, sure you can attack a chloride with another proton, right? But take a look at what you're forming. You know, it's just. And so, no, we stop here. And in fact, in all of these, we stopped there. The only time we did 2 attacks was on a different species. What was the case where we did 2 attacks? Like hydronium attacked 2 species. With H2S, right. Well, it didn't form H2S. I'll tell you, I don't know if I put sulfide on. Did I put sulfide on that exam? Last, I don't think so. Maybe I didn't. But I'll tell you, it happens all the time. You know, people want to keep attacking, so they have a sulfide here. Yeah, it goes to HS minus, and then they want to go HS minus to the next one. But we don't do that. When we do KSPA, we only attack it
before it becomes a strong acid.
Well, H2S, you could, like for example, if I did barium, although barium sulfide soluble, let's do iron 2 sulfide. Iron 2 sulfide, H2O liquid, is going to get it. So the only thing is I'm going to do is I'm going to attack, well, hydronium, actually this you can only do. Hydronium and hydroxide, it's going to yield 2 waters. And then HS minus here. And so here I only attack it once, but in this case, some people will think I'm going from sulfide to this, but it was because sulfide was a very powerful base that it took it from water, not the hydronium. And so this is going to go to H2S and water. And so this looks like I'm actually attacking it twice, but not really. I'm only attacking it once based off the KSP equation. That's what you're going to do here. Yeah, sure, okay, this is a dibasic base, but we only do it if we want to figure out what the pH dependence on this is. We're only going to hit it once. To form bisulfate. Okay, so be careful with that because we don't do this 2 hydronium stuff, even though you'd be tempted to do it. We don't do it. We just add these 2 equations up.
How can hydroxide form and along with HS minus? Right there.
Well, that forms from something else. The hydroxide, well, let me ask, are you good with this so far? And we'll come back to the sulfide. Do you remember KSP double dagger, Kelly? Does that ring a bell? What was KSP double dagger? Think about that, and I'll come back to that. But going back to this, so we need a K value for this. Do you know how to get the K value, you guys?
Combine.
Yeah, the combine method. What was the combine method again?
We know the K for the first and we know the K for the second.
How come the combine method works in this case, but fails in all the other previous cases that we had, multiple equilibria? It doesn't need to be solved simultaneously. That's point 1. All multiple equilibria need to be solved simultaneously, but we get lucky here because we don't have to, right? Because we could use the combine method, which works because. Somebody remind me why the combine method works for this.
Because little is formed and a lot is assumed.
Yeah, exactly. That's good. A little bit of sulfate is formed, and a lot is consumed. How can you tell, Zach? How could you tell a little bit is formed? What clues you into that? A little bit is formed.
A small K for the first one, a big K for the second one.
Yeah, exactly. That's what we want. So we could use the combined method because all KSPs are very small for insoluble species. And this is very large, strong acid. This is actually, this we can get the value for. What's the value for the second equation? Can you just look at it and tell me what it is? We need a number. If we're going to use the combined method, we got to have a number. I'd call it very, very large, but since we need a number, what's the number? How are we going to get it? Whereas in chapter 17, we don't need a number. We don't need a number because if you look at all the problems that we did, and this is a pattern you'll see, if you do a lot of them, and what we do is we assume it's very large, shift the equilibrium all to one side, and then let it re-equilibrate. And so we're actually doing two steps when we really only need one step. But the problem is people don't learn how to reset. If everybody knew how to reset and was comfortable resetting, then we wouldn't have to do 2 steps rather than one step. Okay? But don't worry about it, because in chapter 17 and 16 we solved the problems all the same way. In chapter 18 it's different. We need a number for this, and what is the number? How can we get the number?
1 over K.
No, not KB, but 1 over K A. Right, 1 over Ka for HSO4 minus. I actually know that number.
Why?
1 times 10.
It's a reverse reaction. If you look at the reverse reaction, you see it? HSO4 minus plus water. Acid plus water yields hydronium and conjugate base. Hydronium is sulfate. This is a Ka equation, just written backwards, so it's 1 over the Ka. Saw back in chapter 1. So what is it? What was the question again? What is the solubility at pH or in a pH? At pH what? Okay, at pH 2 means, I want the solubility at pH 2, which means that this is most likely buffered, or we make sure that the equilibrium hydronium is pH 2. And so at pH 2 implies that this must be the equilibrium.
Why can't it be the initial?
It could be the initial. I mean, you know, but if it were the initial, most likely it would have been phrased like this: in a pH. What is the solubility in a pH 2 solution? Well, in a pH 2 solution, you dump it in. That's going to change the pH, though. You know, once you dump that in, right? And so at pH must be equilibrium, so this must be 1.0 times 10 to the minus 2 molar here at equilibrium. And this was 0 to 0, water, ignore. Hydronium, you know, actually, oops, I'm a little offset here. Hydronium we just call initial. We don't even care what the initial hydronium. It could be the same, it might be a little different, you know, but it doesn't matter. But this one's 0, this one's 0, therefore this is plus what? Plus S, S molar. And then we've got to solve for S. How can we solve this for S? We just plug it into our K expression and then solve for S, and then we're done. Okay? So I'll let you finish that.
That is the 1 over the Ka value for the second equation.
Where did I get this?
That is the K value for the second.
This is the power of the hydronium is 2. This is pH 2. So I just converted from pH to hydronium ion concentration, is what I did.
Why wouldn't you use H2SO4 as that solution? I'm curious as to why it's
Because HSO4 minus is like chloride. How strong of a base is chloride? Okay, and 2, you don't even have to worry about it, because I'm telling you right now that we only do 1 at a time. Although you might go, okay, now I'm going to go for a step 2, right? I could go for a step 2 and then include, even though it's going to be minuscule, but we're going to have a problem with step 2. You know, the problem is okay, if I went ahead and I attacked this one, you know, the product that formed here, now the equilibria is going to get quite a bit more complex. And so tell me, what is the number for this? I want to know what the K value. Okay, first, what is the K equal to? This is going to be 1 over the Ka of what? All right, now give me the number. What is the Ka for H2SO4?
1 over very large.
Which is very small. Very
Well, this one's just 1 over very large. Well, I don't want very large, like I said in the previous one. I want the number. I need the number, otherwise I can't make a calculation. you know, I can make an estimate.
1.0 times 10 to the 3.
Where did you get that number from?
I looked it up online.
1.0 times 10 to the
3.
3, and what's the source of that?
I don't remember where. It's acid-base strength table and it's a Ka value.
What are you going to do on a test? You're going to get a Ka chart, and that Ka chart is going to look like, the Ka chart is going to look like this Ka chart here. You aren't going to be able to look it up online, and I don't know what that source is, because 1,000, a Ka 1,000, I don't think that's correct, actually. The last time I looked at but I need to double check that. And that's order of magnitude, I think. But anyway, what are you going to do? Well, conceptually, I don't want to spend too much time on this because we got too far behind. But here, okay, this is going to be 1 over very large. You aren't going to have the number for this. And how are you going to incorporate that? Well, 1 over very large is going to be very small. And so qualitatively, we'll just ignore this, you know? Quantitatively, we'd include it, but if you want to include this into a calculation, all the species, we're going to do that tomorrow. We're going to include all these side species that you probably didn't think about in these calculations, like with sulfate, you know. That's okay. So, you know, the technique is the same. You just attack it one at a time, and if you have multiple bases, you attack each one once, and that's it. That's all we're going to do. In this chapter, we just do it once, not like chapter 17, where we might keep going step by step by step to see what the final result is. Okay. Is that clear? Just hydronium gets 1. Does everybody know that sulfides are different?
Yes.
Why is sulfide different than sulfate? Little is iron. I did iron 2 sulfide. Why isn't it like this? Yeah, sulfide can't exist in water because sulfide will attack water to form HS minus and OH minus. What is the KB for this? What is the KB for this? Yeah, this is the KB, well, we'll just call it very large. Very large, what does that mean? Well, that means, well, I have up here something called KSP, which should look like that, right? And really what I need is, I need the K for this because the sulfide is going to attack the water. So really I should have FES solid plus H2O liquid. This is going to yield Fe2 plus HS minus plus OH minus, right?
Ah, I get it.
Okay, then what is the K for this? Well, it would be KSP times KB, which is equal to what?
But
So
is it
very
1?
small times a very large yields medium or something, moderate. You know, very small times a very large should yield 1. Well, I mean, what does it yield, right?
Mom.
And so what happens is this one is very large. That means sulfide, you know, it's pretty much a one-way reaction, right? One-way reaction. Which means that we aren't going to separate these. We're going to just incorporate them together into KSP, asterisk, double dagger, whatever you want to call it. right? That's going to equal the KSP for barium, or iron 2. Iron 2. Sulfides. So sulfides are different. You just have to memorize that. That's it. It's just memorization. And then what you do with the hydroniums and KSPA, just do a few problems and you'll see. You know, it's a consistent pattern. The same. Okay, does this answer the questions? Yeah. Are there any other questions? And so you would just complete that the previous calculation, just finish it and solve for S. Should be same as what you've been doing. All right. Actually, I was going to show something here, but I'm not.
But what's KSP double dagger?
6 times 10 to the negative 19.
What is the number, or what is the
The number.
6 times 10 to the negative 19? Is that what you got?
Yes, sir. Out of the appendix 2.
Okay. 6 times 10 to the negative 19.
What does that mean?
That's where
What it means is you can solve a ice table now. You know, whatever we want to do. For example, if we want the solubility, we would put in zeros here. Solve for the solubility. Comes out as cubed. If we want KSPA, you know, if we want to know how this changes with pH, then we can do what? What would we attack in the with acid?
HS minus.
HS minus
And hydroxide.
and hydroxide. So we have 2 equations. So we'd be adding up 3 equations for KSPA double dagger. Just like we did earlier. Did I do that in class? KSPA for sulfides, double dagger?
Mm-hmm.
Yeah? Okay. Did I talk about this, double dagger? You know, the HS minus and the OH minus? It's different because you'd expect this to be KSP, but it's not because sulfide is 2, although it's marked on this chart is wrong here.
it's in the appendix as one of those we use also.
Yeah, you use the note B, footnote B. This is wrong. The position of sulfide. So I tried to fix this chart here because it's actually 1 times 10 to the negative 19, which makes it a weaker species than water. And that means that sulfide is a more powerful base than even hydroxide. You know, in fact, it turns out hydroxide is the strongest base that can exist stably in water. And so since sulfide's too powerful to exist in water, we can't have this. This is not possible. It's not possible because sulfide will immediately attack water. It's too strong. It wants a proton, and it's going to take it from water, and it can do that easily because of its strength. On the redox chart, for example, if I asked you to make a 6 molar oxide solution, what would you tell me? I said, you know what, I want a 6 molar oxide. Prepare it for me.
No.
You'd say, forget it, it's impossible, right? If I asked you to make me a 6 molar hydroxide solution, you'd say,
Okay.
sure, I can do that, no problem. But 6 molar oxide, you're fooling yourself. Because oxide's too strong of a base to exist in
Water.
water. You're never going to form it.
Yeah,
Just
I
like
know
if I asked
that.
you to make a 6 molar sulfide solution, you'd say, Forget it.
Oh.
You'd say forget it because sulfide is too strong to exist in.
In water.
You got it? And therefore, this equation cannot exist. This equation does not happen because this sulfide is going to attack the water. Who cares how big Kb is here, because this is the end result, and therefore we're going to measure the solubility based on this equation, not this equation up here. Yes?
Well, what happens if we have ferric oxide?
Fer- Ferric oxide, one, it's insoluble, and two, when it does dissolve, a tiny bit will dissolve, right? But the oxide that goes in solution will not stay as oxide. So if you have rust, Fe2O3 solid, right? This should form Fe3 plus 3 oxides.
Yes.
Oxides. But oxide is too powerful.
So shouldn't there be a 2 in front of that Fe?
Too powerful of a base. So what do you think is going to happen with?
It's going to hydrolyze.
It's going to hydrolyze water. Right? And so do you have the KSP of iron 3 oxide in your?
They got hydroxide, but no oxide.
Negative. You know why? Because they're trying to make your life a little bit easier by eliminating things so they don't have to talk about this. Basically, it's easier to just not talk about it, right? And skip it. A lot of books don't even talk about sulfide. You pull out a regular general chem book, they completely skip or ignore sulfide, or they'll write it like this. There are two things. This is why one of the reasons why we want Petrucci rather than some of the other books, because some books will just leave it like this. Other books will just totally ignore it entirely. And then, which is nice. It makes it easier, you know. But it makes it easier because they figure, 99% of the people don't have to deal with it. But if you're one of the 1% out of the billion people on Earth or whatever, then you might have to deal with it. And we were one of the 1% that dealt with this because we did a qualitative analysis a lot involving sulfides. Not so much anymore, and so maybe we'll ignore this in the future. And like this, you aren't going to find the KSP because they don't want to talk about this. Take up too much space, too many things, too many other things to talk about. But rust is kind of important, isn't it? Yeah, so you would expect that. And so rather than keeping track of all this stuff, because fortunately, somebody else is keeping track. Not just somebody, but a whole bunch of other people are keeping track of all this, and they come up with a database that's updated every year. And this database is for Visual Mintac, and they're on top of it. And so Visual Mintac, which we're going to do tomorrow, Tom Stewart here works for Aerospace Corporation. He was telling me that they had an issue with the cooling system on the space station. They were getting precipitates in the cooling condenser, and they wanted to get rid of these precipitates because they're going to cause damage. And so they tried to model first they got to figure out what the precipitate is, or what the precipitates are. And so they ended up modeling it using Visual Mintac, the cooling system there. And so this was the Visual Mintac was developed by the EPA. It was entirely funded by the EPA, and that's why it's free to everybody who wants to use it. They should do this because most research is funded by the U.S. government, so it would be nice if it were freely available for use. But no, each time you want to get an article, they want to charge you like $35 unless you bought a very expensive, license. Anyway, so oxides you got to think about, like sulfide. Sulfides are quite common in
what?
qualitative analysis that a lot of general chem students do, and so that's why it's included in Petrucci. Okay. Otherwise, they might have just skipped it. Unfortunately, there's too many things to talk about, not enough time, so we've got to skip some stuff. But I don't know why they skipped it. Rust, you're right, that's a good question. Because the oxide. But maybe we'll do it in Visual Mintech. Be an interesting
what?
question.
And rest?
Visual Mintech. Rust, there's another problem with Rust. And how ideal do you think Rust is? I'm just kind of curious. How ideal do you think that is? You guys have a chance to read that one page or 1.5 pages worth of stuff in Chem 1A? How ideal, tell me, do you think this is? Yeah, far from it or close to it? Far from it. Why? Yeah, look at the charges. You're going to have so many other species in there. This will be an interesting one. We'll do this. We're going to put some rust in water and see what happens.
Ooh.
And then you'll see why Petrucci probably skipped this, because this is far from ideal, and we're assuming everything is ideal, and our calculation is going to be total garbage, basically. Okay. It's like the ideal gas law. You're going to use the ideal gas law on some far off planet that's under extreme pressures and low temperatures. No, because your calculation is going to be really bad, probably, because it's far from ideal. Okay. Anyway, any other questions from chapter 18 stuff? Because I need to move on to chapter, the kinetics chapter, 14. No. The kinetics chapter we're going to look at a little bit differently, because what we're going to do, what Petrucci does is he talks about just some generic reaction, like, if we have a generic reaction, reactant A, with a little coefficient A, 3B plus ... this goes to product. We don't, unlike the previous chapters, we aren't going to itemize, because we aren't going to generate a K equation, like a capital K equation for this. But, we have multiple reactants.
Like crystal violet and sodium hydroxide.
Yeah, the problem with multiple reactants is it complicates the kinetics. Think about this. For example, if I cut A in half, if the concentration of A gets cut in half, then most of the time the reaction slows down, because the lower the concentration becomes, the fewer collisions you have, and the slower things get, right? And so normally I cut the concentration A and it slows down. But normally when let's say I cut the concentration A in half and cut the concentration of B in half, both A and B get cut in half, right? Then who dictates the speed of the reaction? Does A dictate it, or does B dictate it, or both dictate it? Turns out both species will dictate it. And so it complicates the kinetics, because let's say, do you recall what first order means? First order means that I double the concentration, the reaction rate doubles. I cut the concentration in half, the reaction gets cut in half. I mean, the speed of the reaction, the rate. So if it's first order in A and it's second order in B, well, what does that mean? Well, B, let's say if I double the concentration of B, second order means I quadruple the rate. There's a square dependence. If I cut the concentration of B in half, the rate gets cut by a quarter. And so there's a square dependence. This one shows a linear dependence, and this one shows a square dependence on the concentration, right? And so now, what happens if I cut A and B in half? Well, if I cut A and B in half, then A says, well, I want to cut the rate by half, but B says I want to cut the rate by a quarter. So what happens? Does the rate get cut in half, or does the rate get cut by a quarter?
No, 8-fold.
And so, in other words, it's like this. If I, rather than let's cut it, let's double. You know, because if I increase the concentration, then the rate should increase, unless it's zero order. You know, when it's zero order, that means no change. But if I double A, then I expect the slope to double. The slope is, you know, how fast. So I expect the rate to double. Right? If I double B, yeah, then I expect the rate to quadruple. So if I double both A and B, then what should the rate do?
8-fold. It's gonna be 8 times faster.
It's going to be, yeah, you're right. It's going to be 8 times. The rate's going to increase 8-fold. So what should I call that as far as order? In other words, this is what we call third order overall. That is a 2 cubed dependence on it. So what's the graph going to look like? Well, here, do you recall what the graph of this looks like? The half-life is the same. Do you remember what this graph looks like? This graph, half-life doubles each successive time, right? What should the graph of this look like now? You know, when I'm charting A and when I chart B. Let's just do a simple, this is A plus B yields product. In other words, can A react at a much faster rate than B? No, I mean, when you look at the stoichiometry, no. They both have to react at the equal rates, because if I consume 1 mole of A, I better have consumed 1 mole of B. If A is reacting faster, then maybe I'll only consume half a mole, but it's not possible to form the product. And so both of these are going to have the same, so it's going to look, well, if the rate increases 3, it's going to be very steep, right? I don't know how this is going to look like. It's going to be different. So, what we're going to do is we're going to make our life simpler. This is how we're going to make our life simpler initially. So let's start off with single reactant reactions. And we're just going to look at this. So well, basically it's going to look like this. A goes to product. There could be some coefficient on this. Yeah, it's a decomposition type reaction. And so the bulk of the chapter, at least the initial part of the chapter, is focused on this. You know, all the graphs and everything else. We're just looking at a decomposition, simple decomposition reaction.
Like a hydrogen peroxide.
Yeah, like hydrogen peroxide, right. That would be a good example. In fact, let's take a look at that. Hydrogen peroxide decomposes into water and oxygen gas. An example of it. All right, and then we're going to describe the kinetics of this. And the way we're going to describe the kinetics is by coming up with the rate law. The rate law for this is, it's just going to be the rate is equal to, okay, now the slope, you know, dA or delta A over delta T is going to come out negative. And we don't want negative rates, so what we do is we'll just take the absolute value of that. If it comes out negative, we'll change it to a positive. If it is positive, we'll just leave it like that. So this will be the rate is equal to the absolute value of the slope. But the problem is the slope might be changing, it might not. It depends on its dependence on the concentration. And so there's going to be some kind of constant here. This is called the rate constant times the concentration of A. Now the concentration of A is going to show up like a 0 order, first order, or second order dependence, you know, where we're going to have M. We don't know because M and A are not the same thing. So M is not equal to the coefficient A. And so where does M come from? M comes from how the reaction occurs. M comes from something called the mechanism of the reaction, which looks at the collisions that are happening in that. And so M, this could be like, for example, if it's first, or let's start off with 0. If it's 0 order, then M is equal to 0. And the rate is just equal to a constant. If it's first order, then M is equal to 1. If it's second order, then M is equal to 2. These are the only 3 scenarios that are going to come up in this chapter for this. You know, it is possible to have other values, right, are possible. But for more complicated reactions. Let's make a little note here. For more complicated reactions, meaning multi-reactant, other N values, M values are possible.
I didn't know that.
So when we're looking at hydrogen peroxide decomposition, let's continue on with hydrogen peroxide. Then we only have 3 choices. The rate is going to equal K times the hydrogen peroxide concentration to the 0, or K times the hydrogen peroxide concentration to the first, or K times the hydrogen peroxide concentration squared. And so it's going to be one of these, you know. Which one? Will it be? And so we're going to talk about, you know, what are all the ways we can figure out what it is. You know, what is that dependence? Probably the easiest method is going to be called the method of initial rates. So what you do is you just measure the initial rate. What is the initial rate? The initial rate is right at the beginning of the curve. We measure the slope. And so if we make a plot, you know, we either want this. We want the tangent, the slope of the tangent at t0, or we want the average slope when less than 5% reaction has occurred. And so let's make the initial molarity 1.00 molar. And so there are two ways we can figure out. But the way we typically figure this out is by just taking a data point. The next data point should be before the molarity hits what? 0.95, because at 0.95, that would be 5% of the original hydrogen peroxide has been consumed. But if my next data point is way out here, I'm a little too slow. Then I can't take the average slope here, because the average slope isn't going to be an accurate reflection of my initial slope, right? Because it's a curve, and so I'll be missing that. And so I've got to make sure I collect data at a very tight interval, and so I can't wait too long. Because the curve might look like this. And so I got to make sure I get that next data quickly, otherwise I'll miss it. And so let's say I'm pretty fast, I collect the next data point here. As long as that's less than less than 5% reaction, I'm good. I can just take the average slope of these two data points and call that my initial rate. Otherwise, I'd have to get the curve and draw the tangent line at time 0 and figure out the slope based on that.
So how many seconds would you recommend?
Well, it could be very fast. Like,
One data point per second.
No, it depends on how fast the reaction is, because if you wait 1 second, it might be already too late, you know? Or, 1 second, you might be at 99.99, only 1% reaction. We don't know, but whatever it is, you got to take a lot of data here, right, to make sure you resolve that. Well, we only care about the initial rate, so we're not going to wait for this reaction to complete, would we? Would you wait until you got 5% remaining, 95% reaction? No. We just need the initial. And so this is what we do with the method of initial rates. We have the hydrogen peroxide concentration. Okay. And we plot that against the initial rate here, or just look at the initial rate here. And so the hydrogen peroxide, let's say, is what 1.00 molar, and then the initial rate we'll call R1. We'll just use either of these methods to figure out, how steep it's declining right at the beginning. And so at this concentration, that slope was this, right? And the rate's going to be, well, the slope's going to be negative, and then we change it to a positive. And then very simply, we just double it. Let's say we go to 2.00 molar, and then we see what the initial rate, this is trial 1, this will be trial 2. The initial rate from 1 versus the initial rate in 2, and then see. If we doubled that concentration, what happened to the rate? Did the rate stay the same? If the rate stayed the same, then
Zero.
zero order. If the rate doubled, then
Second order.
first order.
First order.
If the rate quadrupled, then
Second one.
second order. That's it. That's a pretty easy way to do it, right? Or what do you think?
Yeah.
Yeah. And so, but we have to do 2 experiments. 2 experiments required. 2 experiments, even though they're short, because I'm just doing the initial, I don't want to do it. I just want to do it in 1 experiment. Can we figure it out in 1 experiment?
Why did you experiment?
2 experiments are required because
The difference of.
we got to see what the difference is based on the concentration. When we're only figuring out the initial rate, right? But we need it for 2. Because let me ask you this: after 1 minute, what is the concentration? Do you know? I have no idea what the concentration is. So you know, it's gonna be something smaller, but I don't know. And so this is why I know. Where do I know what the concentration is? At time 0, because that's when I mix everything together. I know what the concentration is at time 0. This is it. I just have to figure out what that rate is. Right? At time 1 minute, I have no idea what the concentration is, so therefore it's meaningless to figure out what the rate is there. Okay. All right, 2 experiments are required. Well, are there other ways to determine? Yes. There are other ways to determine. This is, the only reason this is harder is because you have to do more data analysis. Otherwise, this is easy too. And so maybe I should say a little harder, or maybe a lot harder, depending on, you know, what we do. Maybe okay. We have alternate methods. Alternate methods, I'm gonna just do a bunch of alternate methods here. And so, let's just say, we'll call this A, method of initial rates. B, if we're just interested in the order of the reaction, you know, a method of, well, let me tell you this. 2 experiments are required, can determine M, which is the exponent here, and K. So you can use some algebra to solve for K. If I have a data table here, so I'll just do 1 experiment and I collect data for a while. And so you have hydrogen peroxide here, concentration, and time. Let's see, should I do time first? Yeah, let me do time first, sorry. Time 0, etc. And so here I have my initial, right? And then I find something close to 1/2 my initial here. And then I find something close to 1/4 my initial here. You know, it doesn't have to be exact. This is, you know, qualitative here. Then, do you know what we call the time required to consume half the reactants? We call that T1/2, right? And so when we go from 1/2 to 1/4, we've consumed half of the remaining. And so we look at T1/2 here, the intervals. And so what happened at the intervals here? So for example, if if the second T1 half, let's say this is the first T1 half, this is the second T1 half, looking at the data table. If the second T1 half took 1/2 as long, so the second T1 half equals 1/2 the first T1 half, then do you know what M is? M is a 0. If the second T1 half equals the first T1 half, then M is equal to 1. And if the second T1 half is double the first T1 half, then M is equal to 2. So if we have a nice data table with lots of data, then we can just eyeball it and see how long did it take. So if we started at 1 molar here, we're looking for something around a half. Not half, I mean, if we started at 1, yeah, we'd look for something around a half molar. How long did it take to get to about half molar? And then how long did it take to get to a quarter molar from a half molar? Does that make sense? So maybe I should show you what I mean. Should I show you what I mean, or you're okay with this? So here, method of initial rates is used for more complicated reactions. Here, for example, if we have 0.185, this is going back to method of initial rates, 0.185A here, and we double A, we get 370. And if we leave B constant, so nothing changes with B, if we double A, what happened to the rate? Look, we went from 135 to 270, the rate's doubled. So it's got to be what order in A? If you double A and the rate doubles, then it's first order. Right? So it's got the first order in A. Well, let's look at B here. We got to keep A constant, otherwise it screws things up, because if we double both, then we could get an 8-fold or quadruple or whatever, you know? All of a sudden, the rate's going to be influenced by both, not one. And so here, if we keep A constant at 185 and we double B, so A is the same concentration, so its impact will be the same. We double B, what happened to the rate? The rate actually went from 335 to 13.5. And so the rate actually quadrupled. Do you see that? Rate quadrupled, which means it's second order in B. And so we know it's first order in A, second order in B, and third order overall. So therefore, if we double both A and B, the rate is going to increase. Is it 8-fold? Is it 8-fold? I said 8-fold? It's 8-fold, because if we double A that was to the first order, and we double B, that was to the second order. And so this will be an 8-fold increase. In other words, it's going to be a third order overall reaction. And so, so this should be third order overall. So let's see if we double A and we double B. And so let's look at 1 and 4. We double A and we double B, then this should have increased 8-fold. So 335 times 8, 3.35 times 8. So 3 times 8 is about 24, and we add that, so it's about 27. And so we see an 8-fold increase. Do you see that? Yes? But, you know, what's the graph of this going to look like? The graph is, you know, it's getting messy, right? And so we're going to just keep things simple, and we're just going to look at single reaction right now. Let's see if I can get a data table. So here's a single reactant reaction. You know, A yields products. No other reactants there, so the only thing we have in here is A. And so we start off at A at 1 molar. And so I look around, how long did it take to get up to about half of that? It took about 75 seconds. And so then I'm going to go from about half to about a quarter. How long did it take? Another 75 seconds, which means this is first order in A. Do you see that? You just eyeball it, and just eyeball the data table, and you can see. Fortunately, they collected lots of data here. You know, this shows it. Look at this one though. When we look at this one, we cut it in half. How long did it take? 50 seconds. We cut it in half again. How long did it take? Half as long. This has got to be 0 order. And then let's look at this experiment. We cut it in half. It took 100 seconds. We cut it in half again. We don't have that data, unfortunately, but you can see what happens. Is the half-life getting longer, or is it getting shorter, or is it staying the same? It's getting longer. The first one took 100. Now we're at 150, and we still haven't hit a quarter, which means this has got to be, we only have 3 choices. This has got to be second order. And so we could just eyeball the data and then just figure it out, you know, for a simple reaction like this. But sometimes they don't get a lot of data. Sometimes the amount of data is like this. If you only have the first 3 data points, can you tell me what order it is? You can't tell me by the method I just told you, but can you tell me? Yes. Yes. Now, how can you figure it out? Because, you know, to define a curve, how many data points do we need? No, to define a curve, how many data points do we need? We need a minimum of 3 data points. Obviously, the more data points we have, the less, you know, random error, these random fluctuations. You know, typically we don't want to use 3 data points because if one of those data points was just slightly off, it might change the curve totally, right? But bare minimum, we would need 3. But the thing is, if you took 3 data points widely spaced apart, then you're less susceptible to random error versus 3 data points right at the beginning, right? And so, what are some other methods that we can use to determine? So, let's be from the graph. We eyeball the graph. This is qualitative. We can eyeball the graph by looking at what happens to the half-life, right? Half-life is getting shorter. This is 0 order.
Why is it 0?
We only have 3 choices of graphs. Let's look at all 3 choices and then you'll see. I mean, half-life stays the same. It,
Zero. Oh, wait.
this is 0 over here. This is first. Half-life is constant. This is the concentration of A versus time. Half-life gets longer. Doubles. Draw this curve. Something like that. Half-life doubles, half-life stays the same, half-life gets cut in half. Okay. You're gonna eyeball the graph and see. This will give you M. This is M only, you know? We're only getting M only, not K. This is M only, you know, we just want the, we call M the order of the reaction, or order reactant, order with respect to that reactant. And so M is the order, that's all we're gonna get from this right now. So we can get the order of the reaction quite quickly by just looking at how the reactant is being consumed over the course of the reaction. But let's say we only have 3 data points to define the curve. Let's say I had this data point at time 0. So let's say my data look like this. I can't really eyeball it and then see.
Is that due to the crappy experiment or what?
Maybe.
Crappy experiment.
This is the concentration of A. These are 3 different reactions here. So anyway, we look at this one, and let's say I had a data at time 0. It's 1. Time 0, I have a starting concentration of 1.0 molar. And then at, let's say at time 100, 0.37.
That is a crappy experiment.
At 200 seconds, 0.14. Oh, well, maybe you could see it, huh? You probably could see it, huh? Do you see what order this has got to be?
Can't see it.
You can't see it?
Gotta be double.
That's got to be second order. Or is it?
It's gotta be first order.
Or maybe you don't see it. Do you see it or do you not see it?
I cannot see it.
Can't see it? All right. Or, actually, does anybody see it? Or is it kind of hard to see?
But you want to use half the concentration on that second.
No, I know. I'm trying to make it so you can't see it. How about, sorry, how about this? If I did this, at 25 seconds, we have 0.78. And at 50 seconds, this happens all the time with people. People don't want to wait. They want to leave, you know. I'm not going to wait for the reaction to complete. I'm just going to do this. You know, this is good enough. I got about 39% reaction here. I'm going to get out of lab. I'm going to call it a day, right? And so you collected this much data. Can you see what you got now? No. Now this is kind of hard to eyeball. We can't use one of these easy methods. Well, what are our choices? I could do another experiment, right? But the problem is can I do method of initial rates here? Not really. Well, I guess I could draw the curve here and then draw the tangent, but you know, I can't use the average because the average of these first 2 data points would be too much. reactions occurred, not 5% reaction. It's already, 22% reaction. So I can run another experiment, but I don't want to. I don't want to run another experiment. Can I figure it out just based on one experiment with 3 data points? This is going to be the
Can't figure
collected
it out.
50 seconds worth of data.
50 seconds of data.
Yes, well, it depends on, you got to watch out. We want more data. We want more data. Why? That is, we want to collect more data here because the more data we have, yeah, the more accurate it's going to be because, when you have a lot of data, it averages out what? Or you can average out.
You could say that the one that could be off would be more significant for just a few data points or something like that.
Yeah. Well, we want more data to minimize random error, exactly. There are other ways we could minimize it. Or we need to spread out the data more. If we're only going to collect,
Further apart.
yeah, collect 3 data points at wider intervals. Data collection is overlooked. There's a lot of thought that goes into, conducting an experiment. And data collection is neglected in general chemistry because, the book or the lab manual always tells you what to do. Collect data here, here, here. And then you can easily know, oh, I need to collect data here, here, and here. But nobody ever thinks about it. They don't give it enough thought about, what constitutes a good data set, and, how we get rid of this or try to minimize error and increase accuracy, this kind of stuff. Well, anyway, the other thing is why at wide intervals? Because, at very tight intervals, everything looks linear. It's not until you spread it out, then you can see, was it really linear? Or was it a curve? And if it was a curve, was it like a first order curve, or was it like a second order curve? That's how we can see by spreading it out. And we often do this. If we collect data at the tight enough interval, then we always assume it's linear between those tight intervals, but in fact it might actually be a curve. And so we can, join each of these by a straight line, and it's not going to look too bad, right? As long as the interval's tight. But if we join, a curve like this with straight lines, then it's going to look very awkward. Boom. Oops. Well, anyway, so can we figure this out? Okay, now this is going to be graphical analysis, called. And this is what we're going to do for our experiment as well. We're going to make 3 plots based on the integrated rate law.
We're going to use the visual method tomorrow, but when are we going to graph the genetics data?
Tomorrow. We're going to do
So
both.
we'll be doing both.
Yes. We're going to do both.
How are we going to use visual method? We need to go in lab and do an experiment?
No. It's all on the computer. You don't have to do any experiments. Let me just write the integrated rate laws again here. For 0 order, it's A times t is equal to, it's actually a minus kt. T is the time interval. which is actually delta t, which is equal to t final minus t initial. But t initial is usually 0, you know. Everybody starts at time 0. And therefore delta t is just t final. And that's why we just write t here. This is actually t final. Plus 8 at time 0 initial. And so when we look at the integrated rate law, it's linear. Y is equal to m. M is equal to the negative of the k. K is always positive. Rate constants are always positive. Then t, and then b. So what we do is we plot A versus time, and it's going to come out linear if it's 0 order. If it's first order, this comes out not linear. If it's first order, then we see that ln of A at time t, you don't have to memorize these, I'm going to give them to you, over A at time 0 is equal to minus kt. This is the integrated rate law. And so if we rearrange this equation, and we get ln of A at time t, which is going to equal minus kt plus ln of A times 0. So I just rearrange this using some algebra. And so this is y is equal to mx plus b. And so now if we plot the natural log of the concentration of A versus time, this should come out linear. And so, in other words, an A versus T plot comes out linear if it's 0 order. If it's first order, an A versus T plot comes out nonlinear. Looks like this. You probably can tell just by looking at the curve what order it is, but we're going to assume that we only have tightly spaced data points. If we have tightly spaced data points like this, there's no way you can really tell, can you? But if you have the full curve, then it'd probably be pretty easy to tell. But anyway, we're going to go with LM. If we plot the natural log of A versus T, then this should come out linear, and the slope will be, negative? Yeah, the slope is going to be negative. So this will come out linear. This. Well, that's first. Now let's go to second order. If we go to second order, then we have this as the integrated rate law. 1 over the concentration at time t is equal to plus kt plus 1 over the concentration of A times 0, or the initial A concentration. And so if we make a plot of A versus t, it's going to come out nonlinear. Characteristic second order curve like that. If we make a plot of ln of A versus t, this is also going to come out nonlinear. But if we make a plot of 1 over A versus t, then it's going to come out linear. Actually, the slope is going to be positive in this case. It should come out linear. So this is going to be nonlinear, nonlinear, this is going to be linear. So in your kinetics data, what we're going to do is we're going to make plots of the crystal violet concentration versus time. And then C. We're going to make 3 plots. So we're going to plot the concentration, the natural log of the concentration, and 1 over the concentration, and see which of those 3 plots is the most linear. And the most linear one will tell us what order it is. Okay.
That was better.
Now, once we do that, we can get M.
Well, what if we have such bad data? Can we do it again?
Yeah, you can't do it again, unfortunately, but hopefully your data. Most people have decent data for this, but even if you have bad data, all you need is 3 data points. And so I don't know necessarily.
No, because remember, mine's have come out linear on the first try.
I'll take a look at your data. K, the little k, the rate constant, we can get from the linear plot and the integrated rate law. So for example, if it's zero order, then the k is just equal to negative of the slope. We just figure out the slope, change its sign to positive. If it's first order, then k is equal to the negative of the slope of the ln of a versus t plot here. Just figure out the slope, change the sign here. If it's second order, then we look at this plot, and k is just equal to the slope. You don't have to change the sign. And so this is something we could do rapidly in Excel, correct?
Mm-hmm.
And figure it out based on that. Now, do I have the time, or do I have 3 minutes? 3 minutes, all right. Let me say. Well, on the test, are you going to have Excel?
No.
No. So on a test, we're going to determine it a different way. We aren't going to make graphs on a test. And so on a test, we want to figure out what M and K is for this data, set of data. And so this set of data is going to look like this. Right? How can you tell, is that curved or is that straight?
I can't tell.
And then random error is going to screw up everything. So we're going to assume that there's minimal random error. Otherwise, these results are meaningless. So we assume minimal random error. And so what we're going to do is we're just going to look at the slope of each segment. And so the first segment here, we look at the slope of that and then compare it to the slope of the second segment here. If the two slopes match, then it looks pretty linear, right? And so what we'll do is we'll call this, in other words, we're not really going to look at the slope. It's better to do K, so we're going to do something called K, this is my word for K analysis. And so this first segment, we're going to calculate K1 for that. And then the second segment, we're going to calculate K for this, which we'll call K2. And then C, this is, let's say, the concentration of A versus time. Do that. And then we're going to repeat it for this. We're going to look at the ln of the concentration of A versus time, and then look at those segments here. We're going to look at the first, and then the second, and then figure out the percent difference in the two slopes. And then we're going to do one more thing. We aren't actually going to graph this. We're just going to calculate these. We'll look at 1 over A versus time, and then take a look at those two segments. Since we can't, and it really doesn't tell us much by just looking at the graphs here. And so here, it's easy to calculate the K's. The K we'll just solve this equation for k is going to be a at time t minus a times 0 divided by the time interval. Here, k is going to equal ln of a at time t over a at time 0 divided by the time interval. K, oh, this is going to be in the negative here. This is also going to be the negative of this. K over here is going to equal 1 over a at time t minus 1 over a at time 0 divided by the time interval. Okay, the problem is we aren't starting at time 0. For example, segment 2 starts off at the second time. So instead of calling this time 0, I'm going to call it the initial. So the initial, and the initial doesn't have to be at 0. This is going to be a initial, this is going to be a initial. So for the second segment, we aren't starting at time 0, we're starting at this time here, which is time 25. All right, I'm going to stop here and then we'll finish this problem next time.
Okay, wrap our down tonight. The happy one.
You don't have to prepare for Visual MinTech tomorrow.